Okay, so the title of my talk is Optimal Encodings for Range Majority Queries. So what is an encoding? An encoding is a step further in the idea of succinct data structures. Basically, basically classical data structures aim at best linearity in space, which means that if we call data the worst case entropy of the data in bits, which is, the logarithm of the universe size of object that you want to represent, then you say that your data structure is linear space if it takes order of data bits, and even order of data words is fine, okay? You say that your data structure is succinct if it uses data plus small of data bits, and there exists something called an index data structure, which uses this extra space, but it needs access to the raw data to operate. But the data can be in any other form that gives you some access functionality. And finally, an encoding is a structure that uses this small extra space, but it doesn't need to access the data. So if you want to see it graphically, something like this. Okay, the succinct data structure is little more than the data, but contains the data. Indexing data structure is detached from the data, and encoding data structure has not that. So why is this interesting? Well, you could even delete the data if you know beforehand all the queries that you are going to ask on that, and you have a structure that answers those queries on the data within even less space than the entropy of the data, then you can delete the data, or store it in a slower device or whatever. And that improves efficiency because of the memory hierarchy and less communication, fewer computers if the system is distributed, and so on. And the best example that probably most of you know is range minimum queries on arrays, where even if the array is a permutation and the worst case entropy is n log n bits, you can answer range minimum queries within 2n bits without accessing the array. You use the array to build the data structure, but once it's built, the data structure can answer the queries without accessing it. There has been some work extending range minimum queries to top k and kth, but I will talk about a different problem this time. But first, I had forgotten about this middle slide. With encoding data structures, you have a new interesting question. When you have even succinct or indexed data structures, you have enough information to answer the queries if you have enough time. So the question is, how much extra space I need to answer the query in how much time? Okay, so this is the trade-off. With encoding data structures, you have a new question, which is, how much space I need to answer the query, period. No matter how much time you give me, if I don't have enough space, I can't have an encoding data structure that answers the query. This has been called effective entropy by Golin et al. In 2011. And you can regard it as the entropy of an abstract data type. It's not the entropy of the data. It's the entropy of the abstract data type, right? You cannot reproduce the data. You can just answer a family of queries. So this is the kind of query that I'm going to talk about today. The majority query is as follows. You preprocess an array of elements, and later the queries are of the form. I tell you a range of the array, I tell you a relative frequency, tau, and I want to know which are the elements which appear with more than this relative frequency in the range. Okay? There are small, slightly different variants. I may want to see just one of them, all of them. An important, okay, what could be this interesting for? Basically, for the data mining, you can have a log of activities, and then you want to know, in this time period, which were the most highly visited web page or keywords for searching or words in tweets or whatever. And okay, this problem has been already considered for not too long, but there are a few works about it. And currently, I'm not wrong, the best results is by Belasugi et al. They obtained a linear space, and this time, order of 1 over tau. Remember that tau is a relative frequency. If tau is fixed at indexing time. This is optimal in a weak sense, in the sense that there may be order of 1 over tau answers, okay, tau majorities. But it will take this time even if there is no answer, okay? So this is optimal in a weak sense. And they achieve succinct space, and this optimal time multiplied by log n, even for tau given at query time. So we consider the encoding scenario. And in the encoding scenario, the first thing is that you cannot give, you have to change a bit the problem. You cannot ask for the element, which is the element that is the majority. Why? Because in that case, you can reconstruct the array with the queries, which is the majority in the interval 1 to 1, which is the majority in the interval 2 to 2, and so on. Then you reconstruct the array. So you can't have an encoding data structure that is smaller than the entropy of the data, because you can reconstruct the data. So what you ask is a position. Tell me if there are majorities, and if there are majorities, tell me where they occur in the array. And in that case, you can have an interesting encoding data structure. What we show is that you need omega of n bits if you're required to list for every tau majority one arbitrary position. Okay? The data structure can give me any position. It's not required to give me the first or the last or whatever. If you require the data structure to give you the first, for example, or the last, then it needs more space. Then we can prove that you need, what is it? Okay. Then you need this space, n log 1 over tau. That means that the problem in that case is interesting only if log 1 over tau is a small O of log n, because otherwise you have enough space to store the permutation, or the identities of the elements, not the permutation, sorry. And that also means that no interesting encoding can work for arbitrary tau values, right? Because otherwise it has to work for log 1 over tau bigger than small o log n. Okay, after we submitted the final version to CPM, we obtained improved results that are now archived. So what I will tell you about is directly the improved results. So what we obtain, apart from the lower bound, we obtain an encoding that uses the optimal space, n log 1 over tau, for tau fixed at indexing time. It finds a fixed position, for example, the first or the last. It can give you all the positions of all the tau majorities in this time, which is basically 1 over tau, which is the optimal part, times log n, times a factor that is time of a predecessor query that I will show you later how it comes out. And in the case that 1 over tau is polylog of n, then we'll reach also the optimal time, 1 over tau. The structure is fast to build. It builds in n log n time. And it can also answer queries for tau prime larger than tau, but the time is the same for tau. It is not faster because tau prime is bigger. Okay, first, the lower bound. A way to prove lower bounds here in space is to show that you can encode combinatorial objects and then retrieve them using queries. Okay, to prove that you need n log 1 over tau, a way is to show that you can encode several permutations in an array and retrieve the permutations using queries. Let's focus on one permutation, right? You have this permutation x1, xk. Then you will build a chunk of the array of size 3k. You will set tau 1 over 2k, and you will build this chunk as follows. K numbers that will be unique, then the numbers 1 to k, and then the permutation. Okay? Now you will perform tau majority queries on array, on parts of the array, on range of size 2k. So anything that happens more than once, that appears, sorry, more than once, is a tau majority and should be reported by the data structure. So if you ask this first interval, -1 to k, there are no tau majorities. Everything is unique. But if you go from -2 to x1, then x1 must appear here. If your data structure must report all the occurrences or the first occurrence, then it will report one position here. And from the position here, you know who is x1. The position is x1 if you start counting from here. So you can recover the first element. Now you ask a query from -3 to x2, and you will retrieve x1, which you already know, so you can identify it, and x2, and so on. So you recover all the permutation via tau majority queries. So if you encode n permutations, you will require this number of bits in the worst case, and you can recover them all from an array of this size, n equals 3mk. So if you perform the substitution, you will get n log 1/tau bits. So you cannot do better than this if you are going to answer a fixed position or all the positions. Okay, what about the upper bound? It is better to use this to illustrate. Imagine this example is for tau equal 1/2. What we are going to do, the idea is as follows. You have this array, okay? So you will take each different number, or each different element, like 1, 2, or 3, and you will build, conceptually, the set of all the segments, or all the range in the array, where 1 is a tau majority. For example, 1 is a tau majority here, 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 also here, and also here, right? And nowhere else. 2 is a tau majority only here. If you ask from 3 to 3, then 2 is a tau majority. 3 is a tau majority in many places, okay? Now, what will you do is you will take the union of all those segments, and you will mark them in bit arrays. I have marked here all the positions that are covered by some segment for the 3 here, by some segment for the 1 and some segment for the 2. And another bit vector will tell from those positions that are covered by some segment, which of those are actually the symbol. Which of these are actually 3? Okay, this is covered by a segment, but it is not a 3, so it is a 0 here. The same with the 1 and with the 2. Now, the interesting thing is, if you give me just those bit vectors, I can tell you if the 1 is a tau majority in any range. The number 3, for example, will be a tau majority in any range if, first, there are only 1s in the range. That is, if there was a segment covering all. If there is a 0, then that means that my segment is not a segment where the 3 was a tau majority. Second, when you map that range of all 1s to the m bit vector, bit 1 has to be a tau majority in that range. And this is both queries are easily answered in constant time with rank queries. Rank queries tell you, given a position in the bit vector, how many 1s are there up to that position, and can be answered in a sublinear number of extra bit and constant time. So if you have all these bit vectors and rank queries on them, you don't need anymore this array. You could check one by one those arrays and find which are the tau majorities. Okay, what is the problem? There are two problems. One, there may be too many arrays to try. Now, speaking of time efficiency. Two, there are too many zeros in all those arrays. There are n squared zeros there could be, right? Okay. The good thing is that you can show that there cannot be too many 1s around in the A's. The total number of 1s in the M's is not a problem. They add up to n, of course. But even the A's cannot have too many 1s, because you can prove that any occurrence of this symbol can expand the maximal segments by 1/tau, by order of 1/tau. So the sum of the ones in all the a's is not bigger than order of n over tau. Okay? So the idea is that we can take those bit vectors and coalesce them. And that means that if I have one range of ones here and another range of ones in another array, I can put them together in the same bit vector as long as there is at least one zero separating them. And I can query this bit vector instead of the original ones. For example, here we have coalesced the bit vectors of the 1 and the 2. You have still the blue ones, which were for 1, and the green ones, which were for 2. So because they were separated by at least one zero, you can put them together in one bit vector. And then you can query just this and this. 5 minutes. You won't know anymore which was the number, the actual number that was the majority. But this is good, because if you know that, you have too much information. Okay, so what we can prove is that there are only this number. I mean, if you coalesce the bit vectors, it is sufficient to have just this number of coalesced bit vectors to contain all the range. So basically, the idea is that you will coalesce them, and then at query time, you will query one by one. Okay? And then you will get this time. And if you do the math, you will see that with compressed bit vectors, you can get this space, which is still not the promised space. Okay? But this is actually better than the promised time. Okay. How to reach the optimal space is a bit technical. You basically separate those runs of ones by rough length, and then you take advantage of the length to represent them in better space. So then you reach this space, and you get this extra time for the m's because they become sparse. They become sparse because there are just n ones, but there are n over tau total length. So basically, it's the lower bound for predecessors. So you get this nasty term multiplying your complexity. And OK, the final twist is that if you add n log n bits of space, then you can slash the log n factor in the time. And when 1 over tau is polylog of n, adding this space doesn't change the total space. And in addition, slashing out this time, you get directly the optimal time. The basic idea here is to record somehow which is the coalesced bit vector that you have to query. Not going one by one, because there are too many, but just recording which you have to query. And manage to query only this number of bit vectors, of course. So if you have a short query range, it is sufficient that for any number, for any cell in the array, you record which is the bit vector where the range that covers this symbol, the range that corresponds to this symbol, has been coalesced. So if you have a short range, you check one by one, and you have to check just one bitmap for each position, and this is 1 over tau. And if it is bigger, we borrow an idea from the work of Belasugi et al. We cover the range with chunks of whose size is a power of 2. First one cover, and then the other cover shifted by 1/2 of the length. And it is sufficient to record which are the tau over 4 majorities of each interval, and which is the coalesced bit vector that corresponds. And this is enough. Given your range, you find the smallest of those range covering you. Your tau majorities must be tau over 4 majorities in that guy, and that guy has recorded where are those tau over 4 majorities. So you check one by one all those candidates. OK, this is it. There are several open questions still. The first is if we can reach the optimal time in all cases, or show that it is not possible. Can we reach time according to the tau that is used at query time, not at indexing time? Or lower bound of omega of n bits. Is it just a weak bound, or is the problem actually easier if we are happy with reporting any position, any arbitrary position, and not just the first or all or the last? What about the even weaker problem? I want to report some occurrence of some tau majority. Or lower bound in this case tells you that you need less space when tau is smaller, so that the problem is easier. We don't know if this is because the bound is lousy or because the problem is actually easier and we haven't found how to do it. And of course, if there are other interesting type of range queries. Thank you.
Any questions?
Construction time?
N log n.
Okay.
This is an interesting problem.
Anything else? You're satisfied, right? Okay, thank you again.
Okay.